Welcome back. In this video, we're going to learn about concentration. We're going to define concentration, look at various ways to express concentration, and calculate the concentration for ions in an electrolyte solution. What is concentration? Generally speaking, a concentration describes the relative amounts of two or more things. So in these two boxes, we have small spheres and large spheres. And on the box on the left, we can say that the concentration of the large spheres is equal to the concentration of the large spheres. There's the same number of them in the same volume. However, in the box on the right, you can see that there are many more small spheres than there are large spheres. And so the concentration of the large spheres is larger. Or excuse me, of the small spheres is larger. So that's kind of a qualitative description of concentration. Let's now look at a quantitative description. When we think about chemistry and concentration, this is describing the amount of solute in relation to the amount of solution or solvent. Whether it's the solution or the solvent depends on what unit of concentration we are discussing. There are a variety of units of concentration that you need to be familiar with, and some that you already are. One of those units is mass fraction. This is defined as the mass of the solute per total mass of the solution. We can also describe the mass percent by taking the mass fraction and multiplying it by 100%. The mole fraction, which we've already seen, is defined as the moles of solute over the total moles of the solution. Now, why are these called fractions? Well, a fraction is a ratio of one part of a substance compared to the whole. So in that same way, a mass fraction is looking at one part of the solution, the solute, compared to the whole. And it's doing it in terms of the mass. Whereas the mole fraction is looking at the part in terms of the whole, but using the number of moles. Some other units that we have already talked about are parts per million, and that's determined by taking the mole fraction times a million, parts per billion, which is mole fraction times a billion, parts per trillion, which is mole fraction times a trillion. Or we can describe these by taking the mass fraction times a million, billion, or trillion. So what we see for the parts per million, billion, or trillion, we can describe this in terms of the number of actual molecules or the masses that are involved. A final unit of concentration that we're going to focus on is molarity. Molarity is specific to solution chemistry, and this describes the moles of solute per liters of solution. So again, not only is this solution chemistry, but aqueous solution chemistry, generally speaking. Now, why do we have so many different units of concentration? Well, it's because there are lots of different applications or ranges for which each of these might be useful. When we are talking about the atmosphere, nitrogen and oxygen make up a large portion of the atmosphere. So you can talk about the mass fraction or the mole fraction, and that gives you a reasonable number. However, for argon or carbon dioxide or methane, those are in such small amounts that it makes more sense to talk about it in terms of parts per million, billion, or trillion. Molarity is used when we have aqueous solutions where we have a fixed amount of solute dissolved in a certain volume of total solution. And that's the one that we're going to focus on for the most part in Chem 110. All right, so let's do a practice problem here. We want to know what's the molarity of pure water at 25 degrees Celsius. And we're given the density at this temperature being 1 gram per milliliter. My recommendation when you're converting from one unit to the other is to start by defining the units that you are trying to convert to. So we want to find the molarity. Molarity is defined as the moles of solute per liter of solution. And if we compare this to density, density is defined as the mass of the solute per volume of the solution. So what we need to do then, if we compare these two types of units, is we see that we're converting moles of solute into mass of solute, assuming that our volume of the solution for density is in liters. We can see that we're given it in grams per milliliter, so we know that we're going to need to convert from milliliters to liters. So when we do this, what we see is that we don't know exactly how much of the substance we have. However, if we assume a certain amount, then we can work from that. So let's just assume we have 1,000 grams of water. If we take 1,000 grams of water and we use its density, we see that that's 1,000 milliliters, or 1 liter. This made the assumption of 1,000 grams useful because we end up with 1 liter total of solution. If we have 1,000 grams of water, we can determine the number of moles of water that we have by taking and dividing by the molar mass. This will get us then 55.56 moles. When we divide this by the volume, that gets us the molarity. So our molarity is 55.56 moles of water per 1 liter of solution. Or in other words, 55.56 capital M for molarity. Our next step is to look at the dissolution process and the dissociation process, and remind ourselves that when we have an ionic compound, they dissociate in water to form ions. And this is going to be important because when we calculate the concentration of a substance in water, we need to remember that ionic compounds will dissociate, whereas molecular compounds, with the exceptions of strong acids, will not. So if we want to determine the concentration of ions, if it's a strong electrolyte, then we need to account for the dissolution and dissociation processes. For example, let's say that we dissolve calcium chloride in water. It's going to dissociate into its ions, which is 1 calcium ion and 2 chloride ions. Therefore, if we had 1 molar concentration of calcium chloride, its ion concentrations would be the sum of the individual ions after it's dissociated. So then we'd have a total of 3 molar of ions. All right, let's have you practice now. Which of the following aqueous solutions would contain the largest concentration of nitrate ions? Pause the video and try this on your own. Welcome back. So not only do we need to account for the initial concentration of the substance, but also how they dissociate. Because we're dealing with concentrations, the volumes that are indicated don't actually matter. So for the cobalt nitrate, we have 0.5 molar cobalt nitrate, and we multiply by a ratio of 2 to 1 because there's 2 nitrates for every 1 cobalt nitrate. That means then our total ion concentration is 1 molar. For ammonium nitrate, it starts out at 1 molar, and when it dissociates, we only get 1 nitrate ion per ammonium nitrate. So then our total concentration is 1 molar. For aluminum nitrate, it starts out at 0.4 molar, and when it dissociates, we end up with 1 aluminum and 3 nitrate ions. Therefore, the total ion concentration of nitrate is 1.2 molar. That's it for this video. Thanks for watching. Have a great day.